something like this. Yeah, it seems to be going.
Yeah, I think it is.
All right. So if I just gonna show you the principle. So up here you have the samples. So basically it's an auto sampler with now one has 50 holes. You put the samples, it turns, drops into this, which is a combustion oven. And so when it drops at the same time, or actually 17 seconds after the drop, or before the drop, there's oxygen coming in that mixes with the helium. Helium being the carrier gas that goes all the way to the mass spec, and that allows combustion. So your sample burns, turns everything that was solid into a gas, and then that's the gas you can analyze. The first, so it goes down. Imagine a tube like that one. Actually, I'll show you one here. I should have old ones, I think. No, that's the reduction column. I'll show you. So that's an old combustion tube.
Okay.
See, so you have at the bottom, you got, it's okay. You have, so it's like this. You have at the bottom, you got 4 centimeters of quartz wool. On top of it, you have cobaltic, never remember the name. It's a mix of cobalt and silver. And then on top of it, you have separating it, you have some more glass wool. On top of it, you have chromium oxide. And then on top of it, you put something, I'll do it here. You put what we call an ash collector. So that your sample fall in it, burns in the ash collector, and after a while it's gonna pile up, and you reach a zone of the oven where it doesn't burn anymore. So when you reach that point, you need to take it out and change. Okay? And if you don't have an ash collector, you need to find another way. So the ash collector is just very convenient. It also protects your quartz tubes because I don't know how to say it, but sometimes with time the quartz degrades, and I find that having the ash collector improves the life of your quartz tubes.
So will we ever have to change out the quartz in chromium and silver and stuff?
Yes. Every 2,000 samples on average. And the reason you do it is actually mostly because the quartz is getting tired.
Yeah.
The reagents are still fine. I don't know exactly how long they're fine, but they last longer than the tube. And the reason you do it is you don't want the tube to crack, which causes a mess in there. And then also you lose a tank of helium overnight. Because if you have a crack that starts leaking, you lose a tank of helium, which is 300 bucks. So it's just, you just do it every, I mean on this machine I find that you can push until 2,000 samples, but I don't do samples that are, like if I was doing GFFs all the time, I would do it more often because you tend to destroy that. But the samples I do, I mean I found that 2,000 samples is fine. Maybe I could even push even further, but I'm being conservative and trying to not push it. So that's the combustion tube. So the gas comes out. I'll put this back. doing this because it's not just for education. It's also I'm planning to reuse the reagents. So then it goes here into what we call the reduction tube, reduction oven, which is just copper. It's like that. This one is actually ready to go. It's made of half recycled, half new. That's what I do to be able to recycle some. And just there, it's mostly to reduce nitrogen gases into nitrogen 2, which is what you're going to analyze. So that's what it does. Then it goes into, somewhere in the back, comes out here. Comes out here where you have, this is a water trap. If you don't have a water trap, you won't have a good measurement. The reaction of combustion generates a little bit of water. There is always anyway a little bit of water in your sample, so you need to trap it. If you don't, you won't have good data. So it's magnesium perchlorate. You just put this in there. The gas goes through, and then it goes into your. There's a column. Can't remember the name. That's gonna separate your gases. And so, like it retains CO2 versus N2. How can I say? Well, you know the principle of gas chromatography. The gas goes through the column, and then some molecules go faster, some slower, and at the end you separate your gas into. So this way, once it goes through that, you can go into the mass spec, and then you're gonna analyze first nitrogen and then CO2. When you do both. You can plug this sometimes. That's what is it? The CO2 trap. Because sometimes, especially for samples that have very low nitrogen and a lot of carbon, you cannot do both at the same time. So you need to trap your CO2 to be able to put a lot of material and have a decent nitrogen signal and analyze it. So you put this above the upstream the water trap. I found out that you have to be careful when you do this because that reaction generates tons of water. And the first time I did it for 35 samples, came back in the morning, this had turned into a slurry. That some of it had gone through the tube. I mean, everything was clogged, it was a disaster. So you can use it, but keep this in mind. But mostly for Ryan samples, I've never had to use it because, I mean, he does mostly, well actually amino acid rich tissues. That's tons of nitrogen in there, and that's fine. I've used it for running wood, where the CN ratio is 200.
Yeah.
So at 200, there's no way you can get enough nitrogen. And then.
So right now it's just not connected.
But it's connected. It's going in.
But the CO2.
Ah, this one no. Sorry, this one is not. But everything else is.
Okay.
Yeah, this one is not.
And you would just put the cap on?
You just disconnect, and then you just disconnect, and then connect this one there on top. Put this one at the bottom. I mean, that's just designed to go in between this and that. So that's what you do. You just change the plumbing a little bit, and so you just have to remember that this comes before the water trap. So that's it.